Good morning. Thursday morning here. I'm making a video for you to use as a little bit of a review. I'm sitting on my porch now in Florence, Massachusetts. My neighbors probably think I'm funny to be sitting on my porch and talking at my computer. But we'll get this over with quickly. All right. Oh, yeah. Well, neighbors are walking all over the place today. You're probably seeing that too with this pandemic. So, one more day of remote learning. Here we go. I wanted to review the big ideas. I remember in the beginning of the year, I put them all on the board for you, and I said by the end of the year, you're going to be able to make sense of all these different concepts and topics. But if you're taking the exam next Thursday, you're definitely going to be needing to recognize them. So, let me just go over quickly what they are. There's Phoebe. That's my little kitty Phoebe. And there's a nice little butt shot for you. Okay. So what are the big ideas in physics? We started off with kinematics and dynamics. And the big idea there is, can you see that? Yeah. Equilibrium and F equals ma. So you might have to recognize that an object is in equilibrium how do you know that? So if an object is in equilibrium, it's either going to be moving at a constant velocity or it's not going to be moving at all. And that gives you some really important information. That means that the net force in the y direction has to be equal to zero, and the net force in the x direction has to be equal to zero. If it's not in equilibrium, then you can also add those forces in the x and y direction to find something out about its acceleration. So equilibrium or F equals ma, or equilibrium would be F net equals zero. Big idea in physics. All right, so look for that using your free body diagram. Draw your free body diagrams. Next big idea is conservation of energy. Okay, so if energy is conserved, you might need to state that. If you know there's no friction acting on a system and all of the potential energy is going to convert to kinetic energy, then say energy is conserved in this situation because there's no friction, and then go from there. So conservation of energy is one of those big ideas. Another big conservation law is momentum. So momentum is conserved many times in a collision. If two objects collide, the initial momentum of the system is going to be the same as the final momentum of the system. Kinetic energy might not be conserved, or maybe it is conserved. So if an object is a perfectly elastic collision, that means the kinetic energy of the system before the collision is the same as the kinetic energy of the system after the collision. Most collisions are not perfectly elastic. In fact, if they stick together after they collide, that's considered perfectly inelastic. Kinetic energy is not conserved, but momentum is still conserved. And I see Phoebe back there still. She's so cute. So momentum conservation. Uniform circular motion. Okay, uniform circular motion. What does that mean? Objects are moving in a circle at a constant speed, and so there's something that's important happening for something moving in a circle at a constant speed, and that means that the net force has to be pointing towards the center of the circle, and the net force is the centripetal force. So all forces add, whatever they might be, they add together to point towards the center of the circle, and you can set that net force equal to mv squared over r. So look for constant velocity things moving in a circle, like even planets could be obeying uniform circular motion. All right, so that's a big idea. Simple harmonic motion. Simple harmonic motion is another big idea where another cat, where an object in simple harmonic motion is oscillating back and forth under a restoring force that is proportional to the displacement. That is simple harmonic motion. And so for a simple harmonic oscillator, almost always what's happening, or I should say always what's happening, is there's some potential energy that's converting to kinetic energy and back to potential energy again. There may or may not be friction. Okay. I think I forgot to hold up one of these that were kind of important. Oh, here it is. The work energy theorem. So what does that mean? If work is done on a system, that implies that there's a change in that system's energy. So if somebody applies a force to a system and moves that system through a distance, force times distance times the cosine of the angle in between those two things, you're going to add some energy to the system or potentially take away some energy from the system. Friction always takes energy away. But if I'm pushing a box across a floor that doesn't have friction, I'm probably adding energy to that box, giving it the energy to move. So don't forget the work energy theorem. Work means that an object's energy is going to change. That's the work energy theorem. Okay, so big ideas in physics, you might need to identify those big ideas when you're describing what's going on in a physics problem. I want you to also think about what you've learned with regard to graphs. So area under a curve means different things depending on what you're looking at. And sometimes slope means different things depending on what you're looking at. Use the y-axis and the x-axis units to help you figure out what the slope means and what the area means. So if you take the y-axis unit and you divide by the x-axis unit, that'll give you the slope equivalent. And if you take the y-axis unit and you multiply it by the x-axis unit, that'll tell you what the area means. For instance, if I have a displacement versus time graph, the slope is going to give me the velocity. If I have a velocity versus time graph, the slope is going to give me acceleration. On the other hand, if I have a force versus time graph, the area under that graph gives me impulse. If I have a force versus displacement graph, the area under that tells me about work. And so be careful to look back at those graphs of many different variables and think about what you can get from a graph before you sit for next Thursday's exam. All right, I'm going to put this video on Edpuzzle so that you can watch it. Hope you're all well. I hope you all got your Longmeadow Physics bracelets. And I know Lauren got hers first, and then everybody else's came back to me for an extra stamp. So I don't know, that's just life. Hope you're all well. Have a good day. Bye.